Aloha again, everyone. Welcome to the second part of this lecture on planetary accretion and the boundary conditions on the formation of planet Earth. I want you to rest assured that this second part is shorter than the first part. It's about half as many slides, but as I mentioned in the first part video, I felt it was better to combine this, or instead of having it in one combined video, have it in two separate videos. So this part of the discussion will continue to look at planetary accretion, but now from the perspective of the growth and differentiation of planet Earth, largely at the end or the latter part of the accretion sequence, whereas last time we focused primarily on the early part of accretion, going from condensation into accretion, building up small particles, and then ultimately ending up at a full-size planet. So when we think about the growth and differentiation of the planet, as I mentioned last time, we have these boundary conditions. What was the beginning like? What was the end like? What was happening simultaneously with respect to cooling and collisions and accretion and differentiation? And now we want to think about it from a slightly different perspective, which is what are the conditions? What were things like while we were accreting up to a large planetary body? And there are really three kind of scenarios we can use. The traditional, most commonly accepted scenario is the first one in the list here. It's what we call homogeneous accretion. In its purest form, homogeneous accretion posits that we have the condensation sequence go from high temperature all the way down to a cool material with chondritic type composition, and that then that material starts to collide and stick together and build up a planet so that Earth accretes from a completely homogeneous pool of materials that are all the same composition, and that differentiation comes later. Now, the other end member scenario, which is much less popular, and I will tell you now, generally not accepted as the correct possibility, is something that we call heterogeneous accretion. This is the case where Earth accretes and builds up so fast that condensation hasn't completed, so that in essence, as condensation is happening and we get the very highest temperature phases and then slightly lower temperature and lower temperature and lower temperature, we also start colliding things together and building them up. So the differences in the compositions of the planets might reflect the temperature conditions and the volatility and so forth as we're still cooling. And we'll talk about the pros and cons of this model. And then the other model is something intermediate between these two end members. And again, cutting to the chase, the end member that neither of these end members explains Earth particularly perfectly. Although homogeneous is better than heterogeneous, something that is mostly homogeneous with what I call a little bit of funny business at the end, or a little bit heterogeneity at the end, and in fact, a couple of phases of heterogeneity, as we'll see, is the model that best explains things compositionally, whether it's physically realistic, something that remains to be seen. But when we look at the compositions and types of materials and some of the inconsistencies that we find in compositions of various reservoirs on Earth, especially atmosphere, lithosphere, mantle, and core, relative to both the homogeneous and heterogeneous models, what we end up with is something that says mostly homogeneous with a little heterogeneity at the end. Okay, so I remind you of this picture I showed you last lecture, which kind of includes everything from condensation sequence making little particles coming together, which is the process we call accretion, and at the early stages, sort of slightly metamorphosing so that we go from carbonaceous chondrites to ordinary chondrites. There's radioactive decay there from once live radioisotopes. There's collisional energy being released because of the kind of gravitational energy associated with impacts. Heating, melting, igneous processes, segregation of molten blebs that can coalesce and make a core, so that ultimately we can come to small planetesimals that have a silicate outer part and a metallic inner part, and those look like a differentiated planet. And so the time scale and chemical conditions of that process relative to the rate of cooling at the end of condensation is really the gist of the difference between heterogeneous and homogeneous accretion. Also remember that the iron-rich phase, the dark material in these diagrams, is much denser than the silicate, almost or approximately 3 times as much. And so when we start to segregate the silicate from the iron, and when we have a big enough material to start having a significant gravitational attraction, the denser material is going to sink to the interior, right? And so the formation of the core is one of the key lines of evidence that helps us distinguish between heterogeneous and homogeneous accretion. And remembering back to last time, Goldschmidt's rules and the categories of the different classifications of elements, one of the categories being siderophile, which is iron loving, is also going to tell us something about what we think of our original chondritic uniform reservoir material was segregated into the core. The siderophile elements that are iron loving tend to concentrate there, and the ones that are lithophile and chalcophile that don't like to go into the core end up in the silicate portions of the earth. And the relative proportions from all of the chemical elements that have affinities for either just the core or just the silicate material or some combination in between is part of what helps drive this idea that while most of the core formed after the silicate chondritic material was sort of assembled together, and then we separated into a more silicate-like primitive mantle and a more iron-rich core, that there was also some material being added after that happened, which helps account for having slightly higher than we would predict from chemical equilibrium siderophile and chalcophile element compositions in the silicate earth relative to what would form in a pure homogeneous accretion that was followed after the fact by a pure core formation in perfect chemical equilibrium with all of the silicate material. So this is kind of a snapshot of what the heterogeneous accretion model is thought to entail. Of course, there's variations on the theme, but as it was originally presented by Tarikian and Clark in the late 60s, you have a very, very rapid buildup of a planet. You can see there in the time scales, it says 10 to the third to 10 to the fourth years after the beginning of accretion. It is still hot. We're in a solar nebula that hasn't completely cooled. And so as it's cooling, if we build up planetary bodies big enough, while, for instance, we're just accreting the CAI, the calcium aluminum inclusion refractory material in chondrites, but haven't cooled enough to start to put chondrules and some of the low temperature phases together, then we're going to get a core at the interior of our Earth that's rich in calcium, aluminum, and titanium. It's going to be like a big CAI occlusion. And then as it cools a little bit more, we'll start to get some silicate and some molten iron. Those might density segregate, and then we would start to continue to accrete material onto the Earth that would give us a gradient in composition. Calcium, aluminum, titanium rich at the core, then a more metallic-y iron thing outside of that, and then a more calcium, aluminum, titanium, and iron depleted silicate outside of that. Okay, and that's just not what Earth looks like. If you look on the right side of this diagram, we know we have an iron-rich core, and then we have a silicate mantle on it. And some of the implications of if we were able to condense like the diagram on and accrete like the diagram on the left, and then turn into the diagram on the right, we should still have some of this dense calcium, aluminum, titanium-rich material at the center of the Earth for which there's absolutely no evidence. No seismic evidence, no compositional evidence. So fundamentally, this model has been rejected. It just doesn't really work. The part of it that's quite interesting is that it attempts to build up a planet in just perhaps 1,000 to 10,000 years. And there are some other lines of evidence, which we talked about last time, that suggest that some of the earliest parts of the condensation process and the earliest accretion to make chondritic planetesimals may have been that fast. But we think that the combination of fast with high temperature, which would be required for this heterogeneous model, didn't exist. It may have been fast, but it also cooled enough that as we were building up our planet, we didn't put calcium, aluminum, titanium-rich material at the center. We were able to put iron-rich material at the center. Okay, so there are some pluses of this model, which are that you can explain some of the density differences between the stony planets. And you can also help explain the fact that some of the siderophile elements in the mantle are more abundant than what we would expect from a chondritic mantle that then purely equilibrated between a molten iron component and a silicate component, as I alluded to a couple slides ago. Okay. But we account for that observation in a different way than this because this model has these other problems. And so the other issue I would say about heterogeneous accretion is that it does require a very, very rapid time scale to complete accretion, not to start it, but to complete it. Okay. Now, when we look at the history of impact craters on relatively stable planetary surfaces, such that don't have plate tectonics, for instance, the moon, we see that we're still having very, very large impacts up to about 3.9 billion years ago, right? So if Earth formed at about 4.56 billion years ago, that's a little bit more than a half a billion years of large impacts. Now, these plots kind of show you the time frequency distribution of these things, starting out with a lot of impacts and getting to lesser and lesser and lesser, but having huge impacts still at 0.6 billion years after Earth formed, as is evidenced from the moon, makes it hard to believe that we could have built up to full-sized Earth-like bodies in just 10,000 to, 1,000 to 10,000 years. You can't do both. You can't build up a full planet really quickly and still have large impacts, which would add to the planetary mass, many orders of magnitude of time beyond that. So this is just kind of a reminder of what we think is probably the impact history for early Earth. So you can see time moving across the y-axis, the x-axis, with the oldest time over here. So if you want time to move forward from the formation of the Earth, you'd read this diagram from right to left, okay? And then the rate of impacts, which is deduced from things like counting craters on the surface of the moon and getting an idea of their ages, as well as looking at different materials on Earth and some of the oldest rocks. And we think that there was a very rapid decline of impacts over perhaps the first 100 million years or 0.1 billion years, as reflected by this early part of the curve. There may have been a period of what's called late heavy bombardment. So it started to go down, and then as these planets were sort of sweeping through their ring of orbiting around the sun, they started to sweep up some large objects, and relatively late, we got something that is sometimes called the late heavy bombardment, for instance, as alluded to on the last slide with the sun, on the moon, and then the impacts really tapered off. And you can compare that with the ages of some of the oldest zircon minerals on the planet, some of them being igneous zircons that don't look like they were formed in equilibrium with water, some of them being ones that do look like they were in equilibrium with water. And we will come back to this part of this discussion in a couple of weeks about when do we think we started to have an ocean, when was there liquid water. Since this diagram was made, other people have moved this evidence for liquid water all the way up to very early on in Earth history, at least locally, maybe not a big ocean, but little local areas of water. And so what this presence of these zircons tells us, though, is that we at least had a differentiated crust or proto-continental crust in which these mineral zircon would be stabilized, because it's not stabilized in manolithologies. And so therefore, there was probably a multi-stage process that included the accretion and the differentiation, the building up of a crust and a silicate mantle and a core. This may have happened over a protracted period of time, and we'll get into that aspect in a second, followed by the formation of reservoirs with liquid waters. And everything that's kind of summarized on this slide, and the timescales implied, are too long to be consistent with these kinds of timescales, 10 to the third to 10 to the fourth years. So this is part of the reason, along with the compositional evidence that I gave you, that we tend to reject the heterogeneous model. Okay, so here's a couple of other compositional considerations. If we're building up from a heterogeneous model, we would get a very iron-free lower mantle, has an iron over iron plus magnesium ratio of about 0, because we would be segregating our iron into a metallic phase while it's still hot, not allowing us to have any iron in our silicate. But we know from seismic elasticity, another seismic wave propagation property, that the lower mantle does contain some iron, about 10% in mole fraction relative to magnesium. And that's very hard to do during the heterogeneous accretion model. It also, of course, requires a refractory element enriched meaning calcium, aluminum, titanium, thorium, and uranium, which are heat-producing elements, rhenium and osmium. Lower mantle, which again, we just don't see, okay? It's also difficult to get some of the light elements into the core. As I talked about last time, we know that the composition of the core requires an iron-nickel alloy to have about 10% of something light added to it. The light things, again, the candidates are oxygen, sulfur, silicon, carbon, hydrogen. Some proportion of those things is in there, and you can't really do that if you're segregating to make metal blobs and build that into a core heterogeneously while the condensation sequence is still happening, because the volatiles are not condensing yet at that period of time, okay? It also would predict the heterogeneous model of volatile depleted lower mantle, which is not what is observed. Okay, so I've summarized the minuses here. The compositional ones as well as the timescale ones are primarily why we reject the heterogeneous accretion model. So now let's flip to the homogeneous model. In this model, Earth builds up from cool materials and then heats up from radioactive decay along with accretional energy of the impacts and gravitational energy release, heats up, melts, and then makes a core, okay? So in this model, the heat builds up as the planet accretes. In the heterogeneous model, everything accretes while it's hot with its original heat. Sometime after this, the core forms, and then somehow we have to flip the mantle and segregate all of the metal out of it, which is, you know, an issue that some people have with core formation. This process was probably imperfect, which is how we explain the relatively high siderophile element composition of the upper mantle, as well as having the iron-rich phase not be pure iron, but have some contamination of sulfur, oxygen, carbon, silicon, or hydrogen, which affects the relative siderophilicity of some of the elements, their ability to partition into the core because of those contaminants, as a way of explaining the abundance of those elements in the residual silicate now. But in this model, you can see here that as Earth builds up across a radius starting from left to right of, you know, these are increments of 1,000 kilometers up to its final size, how hot might it be near its exterior skin? Various processes starting out with sort of cool, volatile, and oxidized, becoming more reduced, higher temperature, and even in the red band, getting to the point of volatilizing elements like magnesium and silicon, which we have evidence for, which I mentioned last time, based on things like the iron and magnesium silicon ratio of Earth relative to chondrites and so on. So the other thing that's interesting about this model is it predicts going from a more oxidized to a less oxidized condition as we build up the Earth. This is also another way of allowing us to put some oxygen into the core. As we talked about last time, having some FeO or oxidized iron mixed in with our iron-rich core allows us to lower its density and might help explain some of the density variation of the stony planets, you know, by this process. Okay. It also allows us to consider the possibility that some silicon was volatilized out in this process. Now, one of the main issues in this model, and we talked about, you know, how that would be manifested compositionally last time in the production of primitive mantle compositions, or so-called pyrrolite, which is 90% made of chondritic material that has been melted, devolatilized, and had its iron segregated out, plus 10% more material by mass of just chondritic material, which brings back in some iron and brings back in some volatiles. Taking that, building it up, heating it up, and then segregating the iron out to a core. Okay, that's the whole concept of the pyrolytic model. But how do we do that? Can we make it hot enough in a planet that accretes cool and then builds up heat from accretion as well as radioactive decay? Does it get hot enough to melt the iron, right? Whereas in one of the sort of conceptual pluses of the heterogeneous model is that we never completely solidify the iron, right? Because we start to accrete it to the planet while it's still molten at the end of the condensation sequence, and therefore it doesn't require as much heat to remelt. Okay. So here's the three main sources of heat that come in an accretionary model, and especially one that starts out cool, homogeneous. There's heat from each collision and impact. There's heat from gravitational compression of the body as it builds up in size, and there's heat from trapping radioactive elements, which were much more abundant in early solar system history. Because remember, we just had a nucleosynthetic event right before our solar system formed and our nebula condensed. So we had a lot more radioactive elements back then. They're decaying. And if they're decaying within a planetary mass, then their heat is being trapped. And so we're building up heat inside. We still have heat producing elements on Earth today, but there's way less of them now. So we generate proportionally way less heat. So the question is there enough heat in a homogeneous model? And of course, the slower we build up Earth in the homogeneous model, the cooler things get and the harder it is to reheat them up with these three sources of heat. So there's some trade-offs about how fast could homogeneous accretion be. But as I say, homogeneous is so much better for explaining the compositional attributes that we think that even if it wasn't purely homogeneous, this is closer to the correct answer. Okay. So the positives of this model are that it provides a way to get volatile elements all the way into the core, right? Because it's relatively cool. It provides us a better mechanism to get many of the siderophile elements, the iron-loving elements that were dissolved, with the original in the matrix of the original chondritic material, extracted out of the silicate and into the core. And it provides a heat source for early melting from, the formation of early proto-continents that are associated perhaps in time, based on those zircon evidence I was showing you a few slides ago, with formation. Okay. It's got some minuses though too, right? We have the very lowest temperature volatiles, the most volatile elements. They're kind of a little bit too abundant in the silicate Earth for this model, okay? Because we've got to have all that heat. We got to make that core. We should have lost some volatiles in that process. So that somehow suggests an accretion that in net was a little bit cooler than the kind of temperatures that we would like to melt iron. This is partly why we have this mixed model where it's mostly homogeneous, and then we add some of the volatiles back in afterward, just sort of cutting to the chase and telling you what the actual answer is thought to be. But when core forms, and this may have happened in one stage or multiple stages, we feel like the silicate material that had been present in chondrites melts, heats up, segregates out in iron-rich material, and that's the genesis of the silicate Earth and the metallic Earth, that because the metallic material is denser as it forms, perhaps in an annulus or a spherical material sort of at some depth within the Earth that is hot enough to form, it then collapses gravitationally towards the center. And perhaps catastrophically, perhaps over time, perhaps repeatedly over time. But as this molten iron coalesces, it flows through the silicate material and it strips out the siderophile elements. It pulls some volatile elements with it, and it makes a core of a composition that's most consistent with the kind of core that we have today. Okay. Now, one of the issues with this is, can we build up the heat fast enough? So this is a model showing you the temperature on the y-axis, again, versus the sort of annular ring size or the radius of Earth as it's building up. And it's got an iron melting curve, okay? And that's bracketed by what's called a metal solidus and a metal liquidus. The liquidus is the temperature profile to completely melt the material. The solid is the curve to have complete solid. So if you have what's called partial melt, you're somewhere in between those two things. You can see the iron melting curve runs between them. Now, if we compare this to what we think would be the impact related and gravitational related and radioactive related heat, okay, of accretion as Earth is building up, you can build up Earth fast or slow. That's what the R and the S are here. They're not the R and S process of nucleosynthesis. It's just rapid and slow Earth buildup. We see that the typical slow buildup, which results in the sort of largest late bombardment craters on the moon at 3.9 billion years, that is really not fast enough to ever get hot enough to cross these curves. However, we do get hot enough if we build things up relatively rapidly. So we can have a heterogeneous model. We just barely touch the solidus, but we do touch it. We can melt near the outside of the Earth, not in the interior, but out near the edges, okay? And when that happens, we get a silicate melt and molten iron. Okay, the silicate melt I will be referring to again later as the magma ocean. Some people talk about a magma ocean, other people at the surface of Earth, other people talk about what's called a deep magma ocean, meaning a molten area a little bit in from the exterior of the Earth, maybe a few hundred kilometers down. But in any event, these processes would have to happen simultaneously and in just the sort of right proportion to have it be fast enough and hot enough to reheat our initially cool materials to melt iron, and also to have this iron then settle gravitationally towards the center and equilibrate with the mantle. Okay, this slide just describes a little bit more about what the temperature structure would be and its relationship to the iron melting curve as a function of the accretional energy that's built in. And the traditional idea about how accretion took place and the timescale of it is probably too low or too slow to start making the core very early on in Earth's history. We're going to talk in a second about the timescale considerations about when we think the core formed, right? But this accretional model that's completely homogeneous and then builds up energy slowly would suggest that we wouldn't have enough heat present until about 1 billion years after Earth formed to make a core. And we know from other lines of evidence that the core was formed way before 1 billion years into Earth's history, right? 1 billion years from 4.56 would be 3.56. We think the core was formed much earlier than that, probably in the first couple 100 million years of Earth history. Again, based on things like extinct radionuclides, which we talked about last time. So one possible way of speeding up this process and helping to make the core be able to form earlier is by depressing the melting temperature, making the iron melt better by throwing some oxygen in there, okay? So we can allow the core to form if it's not pure iron, it's iron contaminated with iron oxide that melts at a lower temperature, and that might help us with this early core formation at a time scale and a composition that's more consistent with a homogeneous model. One of the correlations of this is corollaries, as I mentioned before, though, is that you still have to get hot enough to make this iron oxide contaminated iron-rich core to also melt silicate to get what's called a magma ocean, okay? That magma ocean would have subsequently crystallized after the core was segregated and give us our very earliest igneous crust, an igneous crust that was probably more like the crust found on Venus than our crust that we have today on Earth, which is a very dense oceanic crust and a very low density continental crust. The Venusian crust is somewhere intermediate between them, and we would presume that a magma ocean associated with the formation of a core would also have that kind of Venusian-like composition. So this is just a kind of diagrammatic representation of a more recent paper showing you kind of what the kind of relative locations of the forming of a core, the forming of a deep magma ocean, the place where the equilibration between molten iron percolating through silicate would have been, and how this would all have been put together. And there's other scenarios as well, but this model can be consistent with pretty much all the observations. The question is at what depth into the Earth did the sort of DMO, the deep magma ocean, and the segregated metal start to form? Was it very deep or was it very shallow? I tend to believe it was relatively shallow. Now let's talk about some timing considerations of this process. Physical models of accretion suggest that the core formed relatively or simultaneous with accretion, 100,000 years, 200,000 years into Earth's history. We pretty much had a core. It may have continued to grow slowly after that, but the bulk of the core was in place pretty early. We can use lead isotopes, lead being a very mildly siderophile and chalcophile element that finds some small proportion into the core. So we can look at the relative proportion of lead-206, which is produced from uranium-238, and lead-204, which is not a radioactive decay product. It's part of the original nucleus synthetic component in Earth. We look at that in chondrites, and we look at that in very old galena ores, lead-rich ores that formed very early in Earth's history, and then had their lead isotopic composition locked in, okay? And that tells us that we had to have segregated out a core to within about the first 500 million years after chondrules were formed. Now, this time scale is way too long, I think, but at least it was the very first line of evidence that suggested that the homogeneous accretion model, which I was alluding to here, which seems to require 1 billion years of heating to make the core, wouldn't have allowed us to have the kind of uranium-lead variations that we see between chondrites and galena ores. It has to be faster. So another question is, when did we have a crust? The crust would have formed as part of this deep magma ocean. The oldest zircons on Earth, as I showed you a few slides ago, were formed by 4.2 to 4.3 billion years ago. The association of core formation with that early crust seems pretty strong. It seems logical. And so that already condenses our time scale down to saying we probably had a core within 1/4 or maybe, a 1/4 billion or 1/3 of a billion years after chondrite formation. Now, we can also now go to extinct radionuclides, the things that partition, that were still alive when Earth formed, and partition between the silicate and the iron-rich phase. We can make inferences about what we find in the silicate Earth, the rocks that came from our mantle. We can also make inferences from stony meteorites and from the iron-rich phases in meteorites about how things partition between those kind of phases. And from those, we can build up a time scale which is much shorter than this time scale of, 1/4 to 1/3 of a billion years. So there's 4 systems that are really good. I'm going to summarize them on the next few slides that indicate that we had molten iron very early on in Earth's accretion. You recall I already talked about last time nickel 60 to nickel 58 ratios in achondrites, which are differentiated materials from which metal had already been extracted. Okay. And that nickel 60 comes from live iron 60 that only lasted a few million years after the last nucleosynthetic event. That suggests that metal started to segregate from silicate within a few million years of the very earliest part of solar system history. So this is part of this idea that we started to have some segregated metal, and maybe some of that got into a core relatively early. We also have evidence from silver isotopes. Okay, so silver isotopic compositions 107 come from the decay of palladium 107 with about a 6.5 million year half-life. And because silver is incorporated to iron-rich phases more so than palladium, we can look at the relative palladium isotopic composition in the silicate Earth and again infer that some silver was preferentially taken into the core to give us a lower palladium 107 to other isotopes of palladium isotopic composition relative to chondrites in our silicate Earth, again implying a relatively early core formation. There's evidence from chromium isotopes, which result from the short-lived decay of manganese 53. The chromium, again, is preferentially dissolved into iron relative to manganese, is more siderophile. So seeing isotope anomalies in manganese in the silicate Earth again suggests that there was still live chromium when the core was formed, and it stripped out some of that chromium before it decayed. Okay, so both of these two, item 2 and 3 on this list, kind of imply core formation of the silicate Earth, on the silicate Earth, I should say, formed within about 15 million years of the last R process event. So not too long after the timescale of chondrites being formed, which we talked about last time. The final one comes from tungsten isotopes. Tungsten comes from the 182, comes from the decay of hafnium 182. Tungsten is preferentially taken into the iron-rich molten phase of the core relative to hafnium. So the hafnium isotopic composition of Earth's silicate mantle implies there were tungsten that was still alive, that I'm actually saying this confusedly. Hafnium decays to tungsten. So there was tungsten still alive, which gives us a depleted hafnium 182 signature, or less tungsten 182 left in the silicate Earth than we would have expected if the core formed after the tungsten, the hafnium decay to tungsten had been complete. So, and these timescales are somewhere between sort of 5 and 30 million years. So you can kind of see that even though the lead isotope evidence was something like, nearly 1 billion years or 700,000 years, and then there's other lines of evidence that brought it down to a 1/2 to 1/3 of a billion years, and and other things that have brought it down into the sort of millions to tens of millions of years for core formation. And we think this is probably roughly right. And the way we get Earth to be hot enough to be able to melt the iron that early in Earth history from a cool homogeneous accretion model is to allow the iron to have some iron oxide in it, which lowers its melting temperature. Okay. Now, also remember, we talked about that there's about 5 to 10% nickel we think is dissolved in the iron. And we also have the light elements. So now I want to turn to this discussion of what do we think the light elements are? How do we get them in there? How do they fit with this model? How do they fit with the chemistry of what's left? So this is the full list of the candidates. I've talked about many of these in the last lecture. There's 2 elements that are added to this list that I didn't mention before, which are phosphorus and magnesium. I think, you know, mostly we think that the main elements that are in the core that help to lighten it are probably oxygen or sulfur, with lesser amounts of silicon and hydrogen and even lesser amounts of carbon, phosphorus, and or magnesium. But it doesn't have to be only one. But for various reasons, sulfur and or oxygen is the most likely light element. So interestingly enough, the difference chemically in how you partition our chalcophile and our lithophile elements into the core varies as a function of, is our core contaminated with sulfur, which would then tend to draw in some chalcophile elements as we form the core, or is it more contaminated with oxygen, which would tend to pull in a little bit of more lithophile elements, okay? And interestingly enough, again, the iron sulfide and iron oxide are not miscible with each other, so you can't really do both. You either do the iron oxide or the iron sulfide, but you can't really do both. And again, based on the relative proportions of some of the chalcophile and lithophile elements in the primitive mantle after the core formed, we feel it's more likely that the bulk of the light element is oxygen, not sulfur. Okay. So, you know, some of the evidence in favor of the iron sulfide is that sulfur is very depleted in the silicate earth, and it's more depleted in elements with similar volatility like zinc. Also, iron meteorites do contain a large amount of the mineral troilite, which is iron sulfide. Okay, so that's part of the reason why people thought sulfur was it. But these are not kind of definitive arguments. And as I say, the more definitive arguments come from the relative proportions of siderophile, chalcophile, and to a lesser extent, lithophile elements that must be in the core because they're missing from the mantle. So this is a table showing you elements that are both siderophile and chalcophile, a little more of one or the other. Chalcophile being the sulfur-loving elements, siderophile being the iron-loving elements, as a function of volatility. So there's 2 categories here. There are elements that are really involatile, meaning they're kind of refractory and they condense early. Things like cobalt, nickel, rhenium, osmium, iridium, and platinum. And then there are elements that are a little bit more volatile. So they don't really condense at those high temperatures. And if we're making a core at very high temperature, we might lose them back to the volatile phase. These are things like gold, copper, germanium, and arsenic. So we can compare the ratio that we observe or infer from the primitive mantle relative to the core, as well as experiments that are done in labs that look at chondritic materials that are segregated into a silicate and a metal-rich phase. And then we can compare those proportions for both the very involatile and the only mildly volatile, but still more volatile than involatile elements across that range of siderophilicity and chalcophilicity, and infer what the conditions must have been like. And so the diagram on the right side of this thing shows you condensation temperature, as well as the relative abundance between C1 chondrites and what we think is in the silicate earth. And the gist of it is that the siderophile elements are sort of 5 to 350 times more enriched than expected for complete equilibrium between molten iron and silicate, and volatile siderophiles appear to be even more enriched than non-volatile ones. So that tells us that it isn't likely that we had the scenario that was gas-driven, because the volatile ones should be more depleted, not more enriched, if it was primarily driven by temperature. Okay, and that is leaning towards the idea that we were contaminating our core, and yet it wasn't primarily with sulfur, because of the relative proportions of the siderophile and chalcophile elements in these two tables. So that's where we end up in the second lecture, and we'll continue this topic next time. So stay tuned.